Let's look at a couple examples of calculating inverse Laplace transforms. So here's our first one, inverse transform of 2s plus 1 over s squared plus 2. And when you're calculating inverse Laplace transforms, right, the problem is always how do you write the function of s in a way that we can identify it with Laplace transform rules that we already know. So as you do this, you kind of always have to keep in mind what sorts of things do we know come out of the Laplace transform. So things that look like 1 over s minus a constant, this comes out of Laplace transforms, or constants over some power of s, these sorts of things come out of Laplace transforms. Also, two big ones are a over s squared plus a. That comes out of a Laplace transform because this comes from sine. And s over s squared plus a. This also comes out of the Laplace transform. This comes from a cosine. So these are the sorts of things that we want to make appear, or we want to rewrite the function of s as sums and possibly constant multiples of these types of things because we can take the inverse Laplace transform of these. So if you look at this particular example, the denominator actually matches up well with these cases here. Actually, I'm missing squareds here. The denominator matches up well with our sine and cosine Laplace transforms. We just need to make the numerator look right, but you can always do algebra to rewrite this function. And in particular, for this example, we can split the numerator up. So we can write this as 2s over s squared plus 2 plus 1 over s squared plus 2. Okay, so now we can distribute this Laplace transform. And while we're at it, we can also move this constant multiple outside. So 2 times the inverse Laplace transform of s over s squared plus 2 plus inverse Laplace transform of 1 over s squared plus 2. So this first inverse transform, that's going to be no problem. But the second term here, this right here, this 2 right here is playing the role of a squared, which means that a should be the square root of 2. And we were hoping to have a square root of 2 right here. Well, we can have a square root of 2, right? We can have the square root of 2 here if we compensate by dividing this term by square root of 2, right? So since we've multiplied and divided this term by the square root of 2, we haven't actually changed this term. We've just sort of intentionally unsimplified this term so that we can have our square root of 2. So now the second Laplace transform also matches up with one of our known Laplace transforms. So now we can do inverse transforms. So 2 times inverse transform of s over s squared plus 2 is cosine square root 2 times t plus 1 over square root 2 times, and then the inverse transform of root 2 over s squared plus 2 is sine of root 2t. Okay, so the general idea here is for this kind of rational function in your Laplace transform, where the denominator is an irreducible quadratic, you can always separate the numerator so that you can use just sines and cosines to find the inverse transform. All right, so let's look at a slightly more complicated example. So how about this one? This example is more complicated just because the denominator has more stuff in it. We know that one thing you can do with a rational function is write it in terms of its partial fractions decomposition. So there's an s squared term in our denominator here, so that means we need terms in our partial fractions decomposition that have s and s squared. And then there's an irreducible quadratic, that means we need a term in our partial fractions decomposition that has that irreducible as its denominator. And our unknown constants are going to be a, b, and you have to be careful about terms in your partial fractions decomposition that have an irreducible quadratic, because the numerator isn't just a constant c, it's actually cs plus d. Okay. We don't notice that we don't need bs plus e or whatever in this middle term, because this s squared isn't irreducible. S squared is s times s. So this one isn't irreducible. It's only when you have an irreducible, an unfactorable denominator, at least not factorable over the real numbers, it's only in the irreducible case when you get this more complicated numerator in your partial fractions decomposition. Okay, so to make this right, for each piece here, we know if we can only find the constants, we will be able to do the inverse Laplace transform, right? Having an s in your denominator, that's going to give us something times 1. Having an s squared, that's going to give us something times t. And then an s squared plus 1 in your denominator, that's going to give you either a cosine or a sine, depending on whether you have an s or just a constant in your numerator. So if we can only find the values of a, b, c, and d, we'll be all set. So let's do that. So to actually find this partial fractions decomposition, we have s minus 1 over s squared times s squared plus 1. We know that this has to be, for some choices of a, b, c, and d, this has to be equal to a over s plus b over s squared plus cs plus d over s squared plus 1. Okay, now there are many tricks for finding the unknown coefficients in partial fractions. One nice way to start is take this entire equation and clear all the denominators by multiplying everything by the denominator on the left. So we're going to multiply everything by s squared times s squared plus 1. So on the left-hand side, we get s minus 1. On the right-hand side, you have to be careful to distribute this thing and then cancel everything that cancels. But we're going to get s times s squared plus 1 times a plus s squared plus 1 times b plus s squared times cs plus d. Okay. So to find a, b, c, and d, there are a few tricks. So one trick is if you have a linear factor, like here we have s, we can, since this equation is supposed to be true, these are supposed to be equal polynomials, we can plug in any s value we want to get an equation involving a, b, c, and d. So in particular, we can plug in the s value that makes this term go away, and that would be s equals 0. So let's plug in s equals 0. We get minus 1 equals, the a term goes away, this c and d stuff also goes away, we just get b. So now we know b. b has to be minus 1. So that gives us a nice start on solving this. b is minus 1. All right. Another nice trick for finding these constants is, since this equation is an equation of polynomials, right? This isn't just an equation of numbers, it's an equation of polynomials. That means if we multiply out both sides completely, we can just set coefficients equal. So if we the left-hand side is already multiplied out. Let's multiply out the right-hand side. So we have s cubed, as cubed plus as coming from this first part. From the second part, we have a minus s squared minus 1, because we already know that b is minus 1 right here. And then from this third term, we have cs cubed plus ds squared. Okay, so let's, on the right-hand side, let's gather up like terms. So for our s cubed terms, we have a plus c times s cubed. For our squared terms, we have, let's see, there's a d and a minus 1. So that times s squared. For our s terms, it looks like there's just one of them, just this a times s here. And then for our constant terms, it looks like there's only one constant term right here, minus 1. Okay, and now we can set coefficients equal. So a plus c has to be equal to the coefficient on s cubed on the left, but that's 0 because there is no s cubed term. So 0 has to be equal to a plus c. The coefficient on the squared on the right has to be equal to the coefficient on the s squared on the left, but that's also 0. So d minus 1 has to be equal to 0. Notice that now we know d. d is 1. The s coefficient on the left has to be equal to the s coefficient on the right. So that means a has to be equal to 1. So now we know a, we're making progress. And then the minus 1 doesn't really help. If we had not figured out b at the very beginning, then this, the constant terms would tell us that b was minus 1. Okay, so now that we've set all these coefficients equal, notice that we have these equations that are just linear equations in a, b, c, and d. So we just need to solve these for all of the unknowns. So we already knew b is minus 1. Now we know a is 1. We know d, which is also 1. And then this last equation, we can use this to find c. So 0 is a is 1 plus c, so c is minus 1. So a is 1, c is minus 1, d is 1, b was also minus 1. So we need to take the inverse transform of, remember it was a over s, so 1 over s, plus b, which is minus 1, over s squared, plus cs plus d, so minus s plus 1 over s squared plus 1. Okay, so finally we have the partial fractions decomposition. Now we just need to finish off setting things up for our inverse Laplace transform. So inverse Laplace transform of 1 over s, we know that one, that's 1. This minus sign right here, this minus 1 in the numerator, we can move that outside of the Laplace transform as, sorry, the inverse transform, as to make this addition subtraction instead. So now we need inverse transform of 1 over s squared, okay, plus, I guess minus, because we're going to take this minus sign outside of the inverse transform. Inverse transform of s over s squared plus 1 plus inverse transform of 1 over s squared plus 1. So I've split this numerator up into two pieces. The s part of the numerator went into one Laplace transform, and the constant part of the numerator went into another. And now all of these inverse transforms are things that we know. So 1 minus inverse transform of 1 over s squared is just t, minus inverse transform of s over s squared plus 1 is cosine t, and inverse transform of 1 over s squared plus 1 is sine t. So we found the inverse transform of that rational function that we started with. It mostly amounts to doing some big partial fractions problem. If you can rewrite your rational function in its partial fractions form, everything that comes out of partial fractions is stuff that we can use inverse Laplace, stuff that we can do inverse Laplace transforms for.